Hi, and today I want to talk about expression. So for example, recall what we did last time. We started from the variable x and then, for example, constructed 2x plus 6. So this is one instance of expression. And also, I divided by 2, so that's also another expression. And then I can make this expression more and more complicated. For example, like I subtract this expression by x, so that's another the giant expression. And then, so last time, we just realized that this is going to be always equal to 3. Okay? So, we say two expressions are equivalent. If, let me say, two expressions are equivalent if they have the same value. Okay? For so in this case, so no matter x what you substitute, so you always get 3. Okay? So well, so this is just a number, but this is very special. But you could say that, so that's also expression here. Okay? So although it's not, it doesn't involve a variable. So in this case, so this giant expression is equivalent to just a 3 because so this is always equal. Yeah. Okay? So they are always equal. Let's look at another example. Sometimes you can just construct expressions involving more than one variable, like x and y in this case. And it turns out, again, two expressions, 2 times quantity x plus y and 2x plus 2y, so they are equivalent. Then in this case, we say this is an identity. Okay? Unfortunately, for this level, it's just beyond our level to just prove why this works. So, as a college algebra student, so what I recommend you to just accept these basic rules, and then using this basic rule, now you can actually prove more advanced identities. So, for example, let's just check it. For example, just give me a favorite x and y.
7.
X is 7, y 5. Okay, so then let's check. So your left hand side is 2 times 7 plus 5. So this is 2 times 12, which is equal to 24. On the other hand, right hand side, 2 times 7 plus 2 times 5, so that's okay. So both are 24. Okay? But as I said, no matter how many times you just substitute or check it, so it doesn't guarantee it just works for the other numbers. Okay? So that's why this is never going to be the proof. Okay? You're just checking. However, Look at this example. Okay? Actually, this example is a typical mistake students always make. You know? They sometimes just misunderstand this is also an identity. Okay? But the definition of an identity is it's just two expressions must be same for all values, okay, of the variables. So if you want to claim this is not an identity, then all you have to do is to give me just one set of examples for x and y. However, you have to be a little careful. Okay? If you give me the very simple one, then sometimes you still get equal, okay? But it doesn't guarantee that it's just equal for something else. Okay? So that's why you have to give me an example good enough, okay, but not too simple. Do you have any idea? Let's try one pair of x and y. X is 2. Y is 8. Okay, so let's try. So in this case, your left hand side, 2 times 2 plus 8, 2 times 10, which is 20. Your right hand side, 2 times 2 plus 8. So that's 4 plus 8 equals to 12. And then, now you know they are not equal. Okay? So that's why this is enough to claim this is not an identity here. Okay? And this is mathematically just the rigorous, it's a perfectly fine proof. Okay? So to say it's no, so one example is enough. But to say yes, so this is not enough. Okay? So for example, like what's a good example? Like say, if you just give me like x is 0 and y is 0, then just you compute both of them, then you see that left hand side is 0 and also right hand side is 0. Okay? So that's why this case is equal. Okay? But you just pick the too simple. Okay? So that's why you have to pick the something that works here. This kind of the example is called counterexample. Okay? Yes, thank you.